Welcome to the Building Science Podcast.
Welcome to this. Okay. Welcome to the
Building Science
Building Science
Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. Mark your calendars now and don't miss the 2019 ATX Building Performance Conference on May 17th in Austin, Texas. The Humid Climate Conference and friends will be putting on a day-long meeting of the minds to discuss everything from air barriers to the best brisket in Texas, with speakers like Dr. Joe Stiebrick of the Building Science Corporation and Dwayne Donlin, FAIA of the City of Seattle. This will be a heavy-hitting day, and the event will also feature an assembly mock-up rodeo, so get yourself over to humidclimateconference.org now to register. Yeehaw! The Sanden Sanco 2 Gen 3 system is a split-type heat pump water heater system that improves upon the existing high levels of performance and efficiency of the Gen 2 Sanco 2 system. The Gen 3 outdoor heat pump unit uses an R744 CO2 refrigerant to water heat exchanger, but can now produce hot water between 130 degrees and 176 degrees Fahrenheit via the unit control panel. This hot water can then be stored in one of three capacities: 43, 83, and 119 gallons separate storage tanks. The hot water is then delivered via an included mixing valve to supply domestic hot water to the building. The Gen 3 system has a coefficient of performance of 5.2 and can produce 160 degree Fahrenheit hot water in ambient temperatures down below negative 20 degrees Fahrenheit. The heat pump can now be installed at a distance of up to 50 feet from the storage tank, including 16 feet of vertical separation between them. That's a big deal. Installation is simple, with no refrigerant piping and all water piping connections being a threaded type. This unit has an extremely low noise level of 37 dBA, and a video detailing the installation process is available. The systems are listed with Energy Star and is NEEA Tier 3 approved. It's hot water, naturally. To learn more about Sanden water heaters, please visit www.sandenwaterheater.com. Now enjoy the rest of the episode.
Hey everyone, your producer Miguel here. Just a quick word of warning that the audio quality from this episode is not the best, but the conversation is fantastic, and that's why we kept it. We ran into some technical difficulties recording the remote interview, which, if you've ever tried this, you would know it's always a challenge. Anyway, we hope that you enjoy the conversation and that you learn something new about refrigerants.
Okay, hello. Welcome back, everybody. Welcome back to the Building Science Podcast. I'm here, as always, with my sidekick, Miguel. Hey, everyone. And I've also got John Miles on the phone. We've spoken to him before. Say hello, John.
Hey, how we doing? I'm good. How is everyone today?
I hope we're all well. Thank you guys for joining us. So today we're going to be talking about refrigerants, and we're going to be getting into a topic that we call Endgame refrigerants. And I thought we'd start out by just reminding you guys listening that refrigerants are all around you all the time, and not only in your refrigerator, but mainly in the air conditioning systems in your house and car, and in heat pumps that you're using. Where else are refrigerants, John, that we might not realize they are?
Well, I mean, anytime you've got something that's cold, you're essentially enjoying refrigerant from that, right? So, you can go from the super systems that you have at the mega store and where you get your frozen food from, or your refrigerated dairy products, all the way down to the little wheelie bins that have the cans of Red Bull in or whatever, and you pick it up and it's cold. Those have a little compressor and a refrigerant in, they use refrigerant. It's all the basic same vapor compression cycle, but refrigerants, you can name 1,000,001 uses, and I probably still miss a few, but hospitals use it considerably, not just in air conditioning, but refrigerating blood and organs, and you can whip a heart across continents, in a refrigerated bag nowadays and keeping it moving, but it's kept at a temperature, and that all uses refrigerant. Fascinating.
It's interesting how invisible it can go the more common it is. And I think one of the reasons that this is a timely conversation is because of the recent UN climate change report and the recognition that refrigerants are really damaging to the environment.
It's crazy how many pounds or tons of refrigerant are actually out there, right? So, it's something that I think, and I forget the notable author put that refrigerants are probably the number one climate change driver that he sees.
Yeah, that was Paul Hawkins with Drawdown. I was going to mention that book. I also want to remind us that just big picture, right? There's almost this like misperception that people that are concerned about the environment, and whether it's global warming or ozone depletion, that they're somehow saying, what we really need to do is go back to this golden age before electricity, and we all need to live in farms. And that is so not the reality. The reality is electricity and refrigerant systems generally have raised our quality of life, and they're not the issue. The issue with electric generation is unwanted carbon in the atmosphere, and the issue with refrigerants is unwanted depletion of the ozone layer. And there's some other issues we'll talk about. Would you agree with that?
Yeah, I mean, if you look at the rise of air conditioning and you go back to Willis Carrier 100 plus years ago inventing air conditioning and being the godfather of it all, but realistically, I'm sitting talking to you today from Los Angeles. We wouldn't be able to live here, right? Phoenix would be virtually, it would go back to a desert town, right? We'd all be clustered around, areas and nodes where we could, survive, because, you're not going to sit in 115 degree temperature, 120 degree temperature, again, air conditioning in hospitals and, everything that you take sort of for granted in terms of a 21st century life. A lot of that creates heat, and that heat has to disappear. You could argue that, you guys are all listening to this on the podcast, right? Well, that podcast is being hosted by a server somewhere that's being cooled by a refrigerant, and without the server banks and data centers that have sprung up to maintain our internet, none of this actually exists, and we'd be, sending a carrier pigeon out with, very little information attached to its leg, but it'd be enough to maybe get one sentence out of the podcast for you.
All right, that's a good point. Okay, good. So that's the introduction, you guys. Refrigerants, electric energy, they are not the enemy. They just need to be done in a skillful manner. So a little bit more about refrigerant. We talk about this vapor compression cycle all the time, and at the heart of it, vapor compression. So the refrigerants are going back and forth between the liquid phase and the vapor phase. And the vapor compression, excuse me, this is a really bad metaphor, but it's not completely inaccurate. It's like you are compressing the vapor to make a higher heat and have it be able to be shed more easily. And I think of it actually like compressing a sponge, right? You saturate a sponge, and if you squeeze it, if the water were heat, you'd be squeezing the heat out. Tell me how wrong that is.
I mean, that's actually pretty good. The analogy I always try and use is that heat always flows from hot to cold, right? So the hotter you can make something and then put it into contact with something that's cold, you get a lot of heat transfer, right? So what we try to do is you raise the refrigerant temperature up above the ambient in the condenser to reject the heat away from the ambient, right, into the ambient where you don't need it. Essentially that works backwards in the heat pump. And then what you work on is you work on the process of pressure and temperature are intrinsically linked. I think it's Boyle's law. My days of being a scholar are very old, but P1 over T1 equals P2 over T2. So if you reduce pressure, you'd reduce temperature, and that's kind of one of the hearts of a refrigeration cycle or air conditioning or heat pump cycle, is that change in pressure equals a change in temperature, and by manipulating that in various degrees, we get hot and cold scenarios. So your sponge works, because we do try and soak up energy from an electrical circuit. It's not self-perpetuating. It does use the energy from the power grid in some way, and then to compress it, and then hopefully you take the advantage of given by the temperature outside, right? And that's the whole point of a heat pump, is taking heat from one place and pushing it somewhere else.
Well said, yeah. And so specifically on air conditioning, people think of it as almost magic that you can make heat. Well, actually, people don't usually think of it at all. But if they did, they would be like, how am I getting heat out of my house when my house is at 75 degrees? And how am I getting that to flow to the 110 degrees outside? And it's because the refrigerant, first of all, it was lower than 75 when it was inside your house, so the heat flowed into it. And then when it was outside your house, it was much higher than 110, so it could flow out into the 110. I guess that's kind of the heart of the vapor compression.
Yeah, perfect. I mean, that's exactly what we do, and then we just manipulate that cycle depending on what temperature you want and how the actual refrigerant behaves. But essentially, it's just pushing heat from one place to another.
This is a big subject, trying to think about how to approach refrigerants. And since you mentioned Willis Carrier, why don't we start with, do you know the refrigerant he used that was used originally?
Well, I mean, the early refrigerants were all, they weren't really a synthetic style refrigerant. They were ammonia, sulfur dioxide, carbon dioxide, in some ways. Because if you really want to go back to the originals, the vapor compression cycle, the first refrigeration plant, is almost 200 years old. It was developed in 1834. So,
wow.
This is not, as much as it seems like it's new technology sometimes, and things do change just like anything else, cars are 115 years old or 120 years old or whatever they are. They change every year, in terms of technology, but refrigeration does the same thing. So, the original refrigerants were all pretty nasty. Sulfur dioxide is not something you'd really want to run around with, or ammonia, but essentially it was until the 30s that we got what we start to recognize as a real refrigerant, a synthetic refrigerant.
Why was synthetic better?
Simply, well, obviously it wasn't poisonous, right, which is helpful. The idea of the synthetic thing, it's about energy input, right? The old units, just as everything in the past is not as efficient as we have it today. The 1930s air conditioner was plonked in front of us, we'd probably put in as much energy as we would take out in terms of a system, right? So putting in the 1930s the chlorofluorocarbons, the CFC refrigerants, R12, R502, enabled everything to get a lot more efficient, work over a wider range of operation, and really sort of allow that to sort of promote air conditioning or refrigeration systems across, much of the world.
There's a word I'm trying to remember where the pressure range for a refrigerant is stable over a wide pressure range, and it's like a blended refrigerant, but there's a fancy name. Do you happen to remember it?
Oh, azeotropic.
There it is, azeotropic. Yes. So that's another reason why these synthetic refrigerants are superior. They have basically, you just say they have superior pressure temperature properties.
Yeah, I mean, and that's why they were developed. I mean, there are some side effects from them, but you certainly, and then they've moved on from there and evolved over a period of time. And if you look at the actual numbers of refrigerants, there's probably, I don't want to say 1,000, but somebody from DuPont will probably write in and say, no, there's 970. But there are refrigerants that you look at, and, certainly from a manufacturer's point of view, we don't use them because we don't work in that particular area where they specifically work well, right? So some refrigerants work better for refrigeration and freezing. Some refrigerants work better for air conditioning. Some work better for heat pump water heaters. It varies all over the place. So you tend to end up with a lot of different sort of synthetic refrigerants, and it may only have a very small window of opportunity, but it was developed specifically to solve a problem that occurred in terms of a performance or an efficiency number.
Right. That's a really good point. And it just strikes me while you're talking that when we talk about inventing or discovering or using refrigerants, it's this interesting thing. It's not like you find this liquid or this gas and you say, I wonder what it is. Oh, look, it's a refrigerant. No, it's in fact, it's a substance that transitions at suitable temperatures and pressures between a vapor and a liquid.
Yeah, I mean, we could use water as a refrigerant, right?
Right.
Water
Exactly.
boil. You boil a saucepan and you get steam. You put a cold mirror in front of it and the steam condenses back to the liquid, and you can literally do that. There are certain people that have water refrigerant chillers. Kawasaki sells one in Japan, for argument's sake, which is,
Wow.
you can use air as a refrigerant. I mean, have you ever tried sort of, when you're using an aerosol, right? You notice that as you spray it out, your aerosol can gets cold, and that's literally the change in pressure is creating that temperature difference, right? So air, you compress it, it's hot, it has energy. You then, you can expand it and it gets cold. The energy you need to do that then makes a mockery of all the efficiency standards, right? So the trick is to try and find the blend where you don't put so much energy into making the phase change, making it go from gas to liquid or liquid to gas, or compressing it, adding energy to it. And then, otherwise we could all literally sit there and go, okay, you know what, we'll just use air as our refrigerant or water as our refrigerant. But the amount of energy you'd need, and then conversely, the amount of fuel, power plants, et cetera. So it's a sort of interesting scenario, right?
Yeah, exactly. That's where I was going to go. In the distant future where all energy is renewable, we could use, inefficient refrigerant processes without a big penalty. That's not today. So let's jump to today. Let's not go through too much of the evolution of refrigerants leading through the common ones we use today. And I guess let's go to three areas, and maybe we can try to stick to these three if you think it's a good idea. I'm thinking home comfort systems and automobile comfort systems, and then refrigeration equipment. So in homes, what's the dominant refrigerant that's currently used?
So the dominant refrigerant is R410A, right? It comes as different names and stuff like that, which are brand names and stuff like that. But the basic genesis is the refrigerant number is refrigerant 410A, right? It's a blend of two refrigerants, so it's not an actual substance on its own. It actually uses a couple of different refrigerants to make it up. But this has been since about 2006 when we switched away from R22, which is Freon, right? As we call it, because Freon depletes the ozone. 410A is a hydrofluorocarbon. It does not have any ozone depletion on it. So that's the dominant refrigerant. If you go outside and look at your air conditioner, unless it's a pretty old one, it's going to say R410A on it. And that refrigerant's very good at what I call comfort cooling, right? Keeping us as humans, and machines to 70, 75, 72, whatever your specific brand of that is. And then on the heat pump side, maybe 105, 110 degrees, delivered air temperature. It's really, really good at that.
And then conversely, if you're not doing comfort cooling, or I guess let's stick with comfort cooling. In cars, it's also comfort cooling. And is that still R134A?
No, that's yeah. I mean, 134A is coming under increasing pressure globally, so a lot of it is switching to. Well, yeah, Freon again is a term that it just gets thrown around, right? 134A is Freon is actually a trademark of a very large chemical company, so it gets used. It sort of became the trademark for refrigerant. So Freon is actually, it could be called Freon, but realistically, I just always call them 134A, right? So it's a refrigerant. Typically, this is a much lower pressure and temperature refrigerant. It's been used in cars. Realistically, it's probably been the dominant refrigerant, but it's slowly getting phased out. So you're seeing some change in the car industry right now, and a lot of them are moving to a refrigerant, interestingly called enough R1234YF. It rolls off the tongue, but this is a hydrofluoroolefin, if you want to be precise about it, or as we call them, HFOs. Yeah, no, try saying that after 3 beers. Yeah. Right?
Hydrofluoroolefin. I can't even do it before 1. So we have HFCs, HFOs, HCFCs.
So what you're also seeing in some car manufacturers, and Sanden, is leading the way on that, is the use of CO2. Right, so we've now got some vehicles in the European market that are using carbon dioxide as their refrigerant. And as car air conditioning evolves from the typical belt-driven compressor to more of an electric-style compressor, you're going to see some opportunity for CO2 to become a refrigerant there. But again, that's another 7 hours of podcast time.
And I do want to touch in more on that. That's one of the Endgame refrigerants. And the way I want to go there is I want to go through 410A, 134A, and then what was it, 1234YF. Can we talk about those from the perspective of the two, kind of from a broad perspective, two parameters of refrigerants, not within the vapor compression cycle, but separate from that? There's the global warming potential and the ozone depletion potential.
So let's take ODP first, right? Because this is the easy one for us to do. Since, and certainly in the US, since 2006, because of the Montreal Protocol, which was signed in 1996, the developed world, for want of a better term, phased out ozone depleting refrigerants, okay, which were your HCFCs, right? So R22, perfectly fine refrigerant, bouncing along, but it has this little thing where it depleted the ozone layer. So we issued R22 and we switched to 410A for our air conditioning, 134A, which again is an HFC, hydrofluorocarbon. No ozone depletion, again, 1234YF, no ozone depletion. So pretty much any refrigerant that you talk about in the developed world right now is going to have no ozone depletion, right? Which has been a great thing, right? We've stopped that particular scenario. But what we unfortunately did is we exchanged that for global warming potential, right? So all of these refrigerants have a global warming potential, right? And, that's typically we talk about global warming potential in 100-year numbers, right? So it's the amount of damage over a 100-year cycle that refrigerant does, and it's equated back to pounds of carbon dioxide, right? So the number expressed is actually the term of releasing 1 pound of 410A does the damage of around about 2,086 pounds worth of carbon dioxide over a 100-year period. Wow. If you understand my drift on that.
Mm-hmm. Yeah, I want to say it one more time. So the GWP, the global warming potential, is a number that corresponds to the number of times worse than 1 pound of CO2 emitted over 100 years. Yeah,
so CO2 has become the de facto standard for global warming, right? So it's the measurement that we all define it as, right? So you release a pound of carbon dioxide, whether you do that from burning fossil fuels or et cetera, any other process that emits CO2, that causes 1 pound of damage in terms of global warming potential. And it's just because we do huge amounts of CO2, it becomes that sort of scenario there. But if you look at sort of a pound of 410A is going to give you a scenario where it's around about 2,086 pounds worth of CO2 over a 100-year period. That's, again, if you go back to that, it's sort of about the half-life or the damage that it sustains over that period of time. So it's a little bit worse for the environment in terms of that. 134A is a touch better at 1,430 pounds, or GWP number of 1,430. So and some of these other refrigerants can get a little bit more, in orders of 2 or 3, and then you can also look at the number as a 20-year number, in terms of its GWP, and it's not actually, you don't take that 1430 and just multiply it by 5. So for 134A, because it's the one that we talk about most of the time, it's right. 3,790 over a 20-year period. So if you look at it, does that amount of damage for the first 20 years and then tapers on down after that to an average weighted 1430.
And I've heard about these GWPs, and they come out of the IPCC report. There was a second AR and the third AR. These are they do different assessments over time. Tell me about that.
It's not an exact science, right? So it kind of becomes a little bit difficult sometimes to define. The numbers sort of float if you look around. So there is still some work being done on this effect. Just to essentially global warming.
But essentially that we have these existing refrigerants, which are much better as far as ODP, and there's still a lot of room for improvement as far as GWP. What are let's go toward the main topic here, these end game refrigerants. What would you classify as an end game refrigerant? Are there dozens? There's not thousands, right?
I mean, as we progress, we are getting refrigerants with better GWP, right? So one of the great things about 1234YF is its GWP is 4. So it's actually a really good refrigerant in terms of that. Unfortunately, it has some slight scenarios in that it is actually flammable, right? So that's the other thought that you throw in. There's another dimension, right? So it's not always about that. And then typically what you also have is you have the third level, which is naturals, right? Your natural refrigerants. A natural is essentially something that does exist in nature, right? So ammonia is a natural substance, right? Carbon dioxide is a natural substance. Butane, propane, hydrocarbons, all can be used as refrigerants, and all because they exist in the nature scenario have very, very good global warming potential. For example, ammonia or R717 has no global warming potential whatsoever. Zero. Zip nada, right? Propane R290 has a global warming of 3. CO2 R744 has a global warming of 1. So all of these become somewhat interesting in terms of an endgame refrigerant. Now, what you're also seeing is you're seeing other refrigerants pop in, and I think R32 is probably the one that we really sort of talk about in terms of replacement for 410A. R32, it's a blend, has a GWP of 675. So, you might say, 675, we just talked about 4 and 3 and stuff like that. But,
1 and 0,
Yeah, 1 and 0, but compare it to 410A, where it's 2,000 and odd, right? You're actually 70% better than that. So there is some hope in terms of the blend. Unfortunately, of course, the drawback is that R32 is slightly flammable, right? And again, all ends up in, not everything is a perfect silver bullet, as I try and point out to everyone here.
Mm-hmm. Yeah, and we can talk about using CO2, for example, as it's challenging to make that refrigerant process work for comfort systems.
Well, yeah, so CO2, and we do see CO2 being driven into the refrigeration system. CO2 as a refrigerant, the peculiar properties of CO2 is that it works really, really well at keeping stuff very, very cold. right? So your bag of peas or, your bottle of milk, it's really good at doing that. You're seeing a lot of supermarkets out there switching their big plants to a CO2-based system, right? And that's great, and kudos to all of those guys for doing that. On my side of things, CO2 is also a great water heater refrigerant. The Japanese have been using it for almost 20 years as a water heater refrigerant, and it's really, really good at providing you with 150, 160 degree hot water, very energy efficient at that scenario, and stuff like that. So it works really well for heating water. It works really well for doing very cold things below or at 32, 33 degrees Fahrenheit. But you tell it to go and try and do comfort cooling, we're talking about probably 75% less efficient than what you have now as 410A systems, right? So that means they're going to use approximately 3 times as much power as, a 410A system. Now, if you've got power, from the solar, you're making electrons from solar or hydro, maybe that power usage is not so much of an issue, but right here, right now, until a lot more technology goes into working on that, and people are working on it, CO2 doesn't strike us as if I was sitting down and designing a brand new air conditioner for, the year 2030, I wouldn't be picking CO2 as my first refrigerant, right?
Right. You mentioned one of the products, I think it was propane, was extremely flammable, and you said R32 was slightly flammable. Is there a more crunchy definition of flammable or slightly flammable, or?
Well, refrigerant gets designated, right, as a A1, A2, A2L, or A3, right, in terms of its refrigerant world. A3 is highly flammable, right? That's your propanes, your butanes, things that you'd normally associate with putting on your barbecue and heating up your hamburger, right? That obviously is pretty flammable when it comes down to a refrigerant, right? A1 is not flammable at all. CO2 is in that particular scenario, and then A2 has 2 definitions, A2L, which is the lower of the two, and it's all to do with how fast the flame spreads and lower explosive levels, and there's a lot of data behind all of that. Yeah. What you see is people put charge limits on refrigerators or systems using propane, for argument's sake, right? So right now, propane and butane have a charge limit of 150 grams, right? So it's not very much at all, but it's slowly starting to weed its way in, and that's kind of why I brought up the little Red Bull cooler that rolls around. Red Bull does do a lot of natural refrigerants, and a lot of it is actually propane refrigerant in there. So, but because 150 grams is, and again, got to be metrically challenged, right? But it's about, it's only it's 2 or 3 ounces. You're not really going to set the store on fire if it leaks. It's not going to burn quickly. It's more like a mild pop occasionally if it did burn at all, but it's not at a level which would cause an explosion. So the big talk about this right now is raising this limit up to 500 grams. And that, the more refrigerant you have, the bigger systems you can design and move it on from there. So it's going to move to be able to maybe used in mini splits, for example. I think the Chinese guys are going to do or try and put in about 250,000 propane mini splits into the Chinese market this year. Wow. Right? So, your typical mini split that you see outside, 12,000 BTUs, 9,000 BTUs, inverter drive, they are going to use those using propane, which is actually a pretty good refrigerant for it, and try and push that in there. And obviously, then you've got to flare the connections and do all sorts of different things, but there is going to be that propane whipping around the system.
Yeah, it reminds me, actually, thinking about safety and refrigerants. ASHRAE has a couple of standards, Standard 15, which has been around forever, and then Standard 34. even on R410A systems with some of these VRF mechanical systems, you can have large refrigerant volumes, and if they were to ever leak into the space, they could actually displace the oxygen. Like, flammability isn't the only limit. There's this thing you can displace oxygen if you have enough refrigerant leaking into a conditioned space.
410A in that scenario, because it's heavier than air, it sinks to the bottom of the room, right? If you have a small room and all of the refrigerant charge drops into that one room, it displaces all the oxygen, right, without you noticing it, because it doesn't smell, you can't feel it, you can't touch it, right? And then all of a sudden you can't breathe. Essentially that was part of the issue with ASHRAE 15, and certainly, in a previous life as a VRF manufacturer, it was tantamount to figuring out how to deal with that for small, especially hotels and things like that. There was a lot of work done by the manufacturers to solve that issue.
You have a small room with an adjacent refrigerant line that was actually connected to a very high volume of refrigerant.
Yeah, you could essentially drop the entire charge of the entire system into one space if everything, all the stars and the suns lined up in the right alignment.
You are clearly immersed in this field. You're clearly following this, at least as an very interested professional bystander. Where do you see it going? Do you have a crystal ball you can imagine where things are going to go?
Well, I think there's some definite opportunities for the naturals. If I was sitting here and saying, okay, hand on heart, refrigeration systems, whether it's an ammonia system for very large units, cold storage warehouses, things like that, CO2s, the natural refrigerants, those two natural refrigerants have a huge advantage in that space, right? And that's what should be done, right? So, and this goes down to any level of refrigeration, whether it's nip into the convenience store for a bottle of Coke or whatever, that walk-in freezer or cooler that you've got there. It's time that we stop looking at just the capital cost of it and saying, okay, we're just going to chuck whatever refrigerant in we can do. We need to move all of that to a natural CO2 or ammonia in certain circumstances. Water heating, and again, the drive to water heating is, heat pump water heaters have an efficiency above 1, which is the only water heater to do that. Saves us from burning sticks or fossil fuels to make our hot water. CO2 is inherently the best refrigerant out there right now for that. The Japanese have proved that for 20 years. Again, it's a capital cost thing in a little way. New technology always costs more than old technology, right? So, but I'm seeing a will and a push for that into that scenario. The middle ground, that's where the crystal ball gets a little cloudy, right? So probably from a manufacturer's point of view, so this is your air conditioning, right? This is your air conditioning at home and in the office, keeping machinery cool, et cetera, et cetera. So probably an interim solution is going to be R32 rather, just because a lot of the bigger manufacturers, Daikin, for example, are heavily invested in that particular refrigerant, and you can buy R32 mini splits right now over the counter in Australia and other locales. Then we may look at a hydrofluoroolefin. There are others other than 1,2,3,4-YF. There's YE. There's a couple more that I'm sure the wizards at the big chemical companies who make refrigerants are cooking up right now. That, as it takes over the automotive side of things, again, it does have some drawbacks. We see CO2, again, capital cost being what it is. Maybe it works in your luxury sedan, but not perhaps in the baseline coupe or whatever it is. But again, automotive is changing so much because of the push towards electric cars anyway. So that's probably going to drive a lot of different issues in the automotive air conditioning sphere in there. So, when it comes to stationary cooling, if I put my hand on my heart, I'm rooting for 290, but it's not going to happen just because of the inherent dangers of it. right? Until we can work out something. So I think maybe that one's, as I say, there's a good middle ground to step to. It may not be the perfect solution, but 32 is probably going to be an interim solution. Right. And then, as work continues on, making propane safer, increasing the efficiency of CO2, those have the opportunities. But I think the end game with refrigerants is going to be a drive to naturals. Right, go nat refs, go natural refrigerants, right? Because they do the least amount of damage, and if we can figure out some of the operating and cost penalties that we need to do the right thing, then they make inherent sense to do that. However, as I say, there's probably some guy in a lab somewhere locked up in wherever that's on the verge of creating his own perfect refrigerant that hopefully does everything. It's super efficient, has no ozone depletion, has zero global warming or very little global warming. It's not flammable. It's not carcinogenic. It's,
Wow, I got two wrinkles for you. One is, for space cooling, it seems to me that one of the issues is the moderate temperatures that's needed indoors that our bodies are comfortable in. Well, for heating, both heating and cooling, if we use hydronic-based systems, we could store the hydronic fluid at a much lower temperature and mix it up to space temperature comfort ranges.
Yeah, so that's one of the scenarios that you can look at is that, so do we suddenly abandon our mini splits and our central air systems and go to a hydronic chiller outside, right? Because chillers exist, right? Big buildings have chillers,
and single phase exist,
and small chillers exist, and certainly a lot of other marketplaces. This monoblock water heater, which exists outside of the ambient, outside of the envelope per se, right? So it can have a flammable refrigerant in it if it wants, because you don't put the refrigerant into the building and we just pipe water around. So so the rise of hydronic, you're seeing it in Europe. Huge numbers of these monoblock style systems going in, and you can do cooling, you can do heating. So you can do a lot of different things, and with the rise of heat pump performance, the adage is that you don't have to worry now. We can provide hot water in the frozen tundra of Minnesota, and
very efficiently.
You don't have to. You can do it efficiently, and we can get the water temperatures that we need out of that air. So those have some opportunity, and there's a big opportunity for that. And I'm a big proponent of that product. It's definitely something that I think that the U.S. is well overdue for.
I think so too. I mean, as far as elegant thermodynamics, there's an air-to-water heat pump, right behind me here on this wall, and it's a fantastic system for both heating and cooling. I'm curious, could you tell our listeners what you meant by monoblock systems?
Monoblock is something that we use, and it means that the system creates hot water or cold water, and then that water is then pumped into the building, right? The other style units, the long departed and missed Daikin Altherma unit, right?
Right.
That had the ability to have you punched in refrigerant lines, and then there was a refrigerant to water heat exchanger module that you put onto it, and then you had air conditioning, which was fed by refrigerant 410A. That's the other style of system, but that really doesn't solve our issue in terms of flammable refrigerants, low global warming potential refrigerants, and stuff like that. So the monoblock is sort of, I guess you could call it a heat pump boiler if you wanted to, right? Or a heat pump water heater is. We've used that term before.
So it can be used for space cooling or heating and making hot water, and the refrigerant is always contained within one package.
Yeah, that lives outside and just hums away doing what it does.
Yeah. So my air-to-water heat pump has two of those characteristics. It's the refrigerant never leaves that box, just the water, but it doesn't make hot water directly. I mean, it does make hot water directly, but not when I have it in cooling mode.
Yeah, so there are some challenges, and there are some things that we're all working on and stuff like that. So there are some abilities to do that. There's a company called Miyakawa that has a very large CO2-based system that works very well for hotels, and it makes hot water, it makes cold water and things like that. So it's but it's on a large scale system because it always wants to have a building where it has some cooling load. The technology exists. It's just a case of, like I say, there are, I think 7 million or 6.5 million that I have to look at the latest shipments of air conditioners and heat pumps into the US this year, right? So that's a huge flywheel of product to slowly change out, right? You can't literally just lower the boom on them and say, okay, as of 1st of January 2019, we're not doing that anymore, lads. Right?
It doesn't make sense, so let's stop.
As much as we'd like to change out some of these old inefficient industries, and there are better ways of making hot water than burning sticks, as I say.
Yeah. But things do change, and I think a lot of what you just forecast is probably going to come. The other wrinkle that I was thinking of, and I don't really know much about this, but there are solid state cooling systems out there, like the Peltier effect, and who knows what wizards are working on those these days. Because I know for electric vehicles particularly, one of the big challenges is, air conditioning in that electric vehicle. It's a big energy suck.
Yeah, I mean, the other thing that you can throw out there is some of this phase change material, right?
Right.
That there's a lot of work being put into those. I would not characterize myself as anything but an interested bystander on those things. But yeah, I mean, also electric vehicles, right? I think you'd all be shocked to find out how many BTUs actually go into cooling your car. The number is actually mind-boggling when we think about a home, right? And you've got, I've got a 48,000, I've got a 4-ton air conditioner on it. Well, you're driving around in this box and it's probably got something that's a little bit bigger than a 4-ton air conditioner compressor strapped to it. There's a lot of heat load, there's a lot of glass. Sits out in the sun all day. There's a lot of metal. There's not much insulation in terms of anything like that. So there's a significant cooling and heating load required from your automotive box that you've got to be able to account for. So in an electric car, if you want to sit there and run your Tesla with the air conditioning on all day, your battery life just disappears to whatever, right?
Yeah, one of the fundamental differences is your house doesn't need to overcome fluid resistance. So your car, since it has to go fast and move a lot of air out of the way, and you have friction, the air conditioning load, if you have an internal combustion engine, is actually relatively small compared to the other loads of the car. Gravity, going up and downhill and accelerating. And
that's a whole new science, right?
Yeah. Okay. Wow. I think that was a feast of ideas. Is there anything else you wanted to cover that we haven't touched on?
No, I think we kind of rolled through pretty much 200 years of stuff in about 50 minutes. So that's pretty good, right?
It's really good. Yeah.
As I say, if you want to drill down and we can talk about naturals in some much more depth as to how those work and the vapor compression, we can do that. But, there's a lot of different nuances and encourage everybody, if you're really interested in refrigerants, there's a lot of great things out on the web now that you can Google and go through and look at refrigerant operation and stuff like that. So yeah, it's been great.
I think this is a good place to stop. Otherwise, it's going to be a 6-hour episode, as you say. So thank you so much, John. Appreciate your intelligence and your clarity, and thank you all for listening.
No problem. Thanks a lot, everybody. Bye.